Hi again, hope you're having an awesome day. Today we are going to talk about Le Chatelier's principle. So, Le Chatelier was a French chemist, Henri Le Chatelier, and he studied equilibrium reactions and introducing stresses to these equilibrium reactions. So, what that means is he would start a reaction, allow it to reach equilibrium. Remember, equilibrium means that the rate of the forward reaction is equal to the rate of the reverse reaction. And then once they've reached equilibrium, he applies a stress to that equilibrium and sees how the reaction proceeds. So Le Chatelier's principle says, if stress is applied to a system in equilibrium, the system shifts in the direction that minimizes the effect of the change. So what does that mean? Again, if you have a reaction that has reached equilibrium, so let's say you start out with your reactants, it's a reversible reaction, you end up with products. Each reaction is different, and each reaction will have, at equilibrium, a different ratio of reactants to products. So if you remember when we looked at, in the last video, the concentration versus time, and we said reactants, you start out pretty high, and then they decrease over time, and then they remain steady. Products start out at 0, obviously, because you don't have any products to start with, and then they increase as the reaction goes, produces products. They increase, and then they remain steady. And those products could be higher or lower than the reactant concentration, but they do not need to be the same. So let's say it looks like this. So then, these are my products, and these are my reactants. And here I have reached equilibrium. I know that I've reached equilibrium because the rate of the forward reaction is equal to the rate of the reverse reaction, and I know that because the amount of products remains constant, the amount of reactants remains constant. They're not equal to each other, but they are constant. So, since they are remaining the same, the products are not changing, the reactants are not changing, because every time I make a reactant molecule, I go and make a product molecule. So my numbers don't change. Because of that, my ratio of products to reactants does not change. Again, because your rates are equal. Well, what if you've reached equilibrium, you've reached this, and then I introduce some kind of stress? Stress means I change the concentration, I change the pressure, I change the temperature, I heat my solution, I put it in an ice bath, something like that. Then, because we've disturbed it, it is no longer at equilibrium. What does that mean? That means my rates, my forward and reverse rates, are not equal anymore. We introduce a shift. That means either my forward rate is going to be higher, so my forward reaction is going to happen faster than my reverse reaction. We say that that's shifting to the right, to go from reactants to products. Or the other way could happen. I could make it shift to the left, meaning that the reverse rate, going from products to reactants, is higher than the rate of going from reactants to products. Let's say that you stand up and you're at equilibrium, with your weight, and then somebody pushes you forward. What do? You lean backwards to shift your weight so that, you overcome that stress. And so if I introduce more reactants, for example, it's going to shift to the right to use up those reactants. So it minimizes the effect of the change. So let's look at what kind of stresses can be applied and how the system reacts to that. So the different things that could stress my reaction would be either a change in the concentration of the products or the reactants. So I can add more reactants, I could take them away, I could remove the products as they form or something like that. I can change the temperature, can heat it, can cool it, or I can change the pressure, and this is only going to affect gaseous species. So let's start with concentration. So this says adding more reactant produces more product, and removing the product as it forms will produce more product. That's good and all, but that's kind of hard to kind of visualize. So let's look at an example. So I have A reacting with B to produce C and D. So let's say your reaction reached equilibrium. The forward rate is equal to the reverse rate. So every time I use an A and a B to form C and D, a C and a D gets used up to form an A and a B, and so my reactants and products remain constant. So what if you're already at equilibrium and then I add extra A? Now I have too many reactants, too much A, right? Well, that's not right. That's not the ratio that I want. So what do I do then? I need to somehow use up that extra A that I added. So to use up that extra A, to get rid of the extra A, what happens is it shifts to the right. So that means the forward reaction becomes faster than the reverse reaction until eventually it reestablishes equilibrium. So because I have extra A, it's going to shift to the right to use up that A and get rid of the extra A. And so let's write that down. We would say it shifts right to use up the extra A that I added. Okay, what if I remove some B? So if I'm at equilibrium, ratio is great, and then I take away some B. Well, now you don't have as much B. What do? You go in the direction that would make more B to make up for whatever you lost, right? So what direction would make more B? Left. If I go left, then I make up more B for the B that I lost. So we'll say shift left to make more B. So you go in the direction that would minimize the effects of the change or the stress that you're applying. Okay, what if I increase the concentration of C? So again, I'm at equilibrium, everything's great, but then I add some more C. When I have too much C, I have too much product, right? What do I do to get rid of that extra product? I shift to the left, use up my product to make more reactants. So this one is going to shift left to use up the extra concentration of C. Okay, how about what if I decrease D? That means I'm removing some of that product. Well, now I don't have enough product, so it's going to shift to the right to make up for the lost D. So that's how concentration affects the equilibrium position. Let's take a look at the next stressor, or type of stress that I can add. I can change the temperature. So I can put in an ice bath or a hot bath or something like that. So when you increase the temperature, that causes the equilibrium position to shift in the direction that absorbs heat. What does that mean? Let's look at an example. So let's take a look at this first example here. A plus B reacts to yield C plus D again, and it also produces heat. So this is an exothermic reaction. How do I know that? Because heat is being released, or it's in the product side, right? So what if this reaction was heated? That means I'm adding more heat, right? Well, if I add more heat, the heat is on the side of the products, right? I have too much heat now because I heated it. So which way would it shift to remove some of that heat? It's going to shift to the left to use up some of the heat, get rid of it, and it moved to the left. So shifts left. To use up extra heat. All right, let's look at the next one. What if the reaction was cooled? Well, if I cooled it down, that means that I'm decreasing my heat, right? Cooling it down, removing heat. So now I don't have as much heat. I'm removing some of the heat, right? So I have too little heat. But what do I do to make up for that? I go to the right to make more heat. Shifts right to produce more heat instead of the heat that I lost. Let's look at the next one. In the next one, same type of reaction. This one tells us delta H is equal to 80 kilojoules per mole. Notice that delta H is a positive value, which tells us it's endothermic. So if they don't give you heat in the reaction, in the equation, you want to write it in the equation. If it was exothermic, you put it in the product side. If it's endothermic like this, then you put it in the reactant side. So I'm going to here say plus heat. Because in an endothermic process, heat is absorbed. It's added in with the reactants to produce the products, right? So this time, let's say that I heat up my reaction. And so if I heat up my reaction, that means that I'm adding extra heat, right? Well, I don't want that extra heat. You're disturbing it. It was already at equilibrium, it was already good, and I have too much heat by heating it. So what do I do to get rid of that heat? I make it shift to the right to use up the heat. So shifts right to use up heat. Okay, what if I am going to cool it down? Well, if I cool it down, that means I'm removing this heat. And so it was already at equilibrium, and now I'm cooling it. I'm removing some heat. What do I do to make up for that lost heat? I shift to the left to make more heat, to produce more heat. So notice that if it's exo versus endo, the shifts are kind of opposite because the heat is on opposite sides of my equation. One last thing that produces stress to your system at equilibrium is pressure. And pressure affects only gaseous particles, and it's only a stress if it's caused by a change in volume. So if I change my vessel volume, that changes the pressure, and therefore it produces a stress. If I change the pressure in a different way, then it really does not affect the equilibrium position. We'll talk more about that next year in AP, or you'll talk more about it in college chemistry if you take it. So pressure, remember, has to do with collisions of gas particles. So if you increase the pressure, you are going to shift in the direction that has fewer gas particles, because if you have too much pressure, if you increase the pressure, that means you have too many collisions. So you want to go to the side that will make it less collisions, because you have too many collisions. You want to go to the side that has less collisions, which would mean the side with fewer gas particles. And obviously the opposite would be true. So if I look at this reaction here, I have N2 plus 3H2 going to NH3. That is a reversible reaction. Here, I forgot my other arrow. And so if I increase the pressure, that means I have too many collisions. So it's going to shift to the side that has less gas particles. And so if you look at this, we have 4 gas particles here, 2 gas particles here. And so I'm going to shift to the right to minimize those extra collisions. If I decrease the pressure, that means I have too few collisions. I don't have as many collisions. I want more. So which side would it shift? It would shift to the left, the side that has more gas particles, so that I get more collisions. Now let's look at an example. With a lot of reactions, you can't really tell that the reaction has reached equilibrium because a lot of times our reactants and products as well are either like colorless solutions or white powders or something like that. So a lot of times we can't really tell where we are in the reaction, if we're at the beginning or at equilibrium or where we are. But there are a few unique reactions where there is a change in color or something macroscopic that we can observe so that we're able to tell. And so this is an example of a reaction like that, where they're all solutions or liquids. My reactants and my products are either aqueous solutions or liquid water. And so in that aspect, you can't really tell. However, they are different colored solutions. So my reactant here, this is pink, this is colorless, this is blue, and this is obviously colorless. So colorless with pink, that makes my reactants pink. Blue and colorless obviously makes my products blue. And so when this reaches equilibrium, remember you're going to have at equilibrium some products and some reactants. So it's going to be some shade of purple, right? Depending on, do you have more products at equilibrium? So it's going to be more bluish purple, or more reactants at equilibrium, so it's going to be like more pinkish purple. So when we do get a shift in our equilibrium position, we'll be able to tell by looking at the colors. So I wanted to do this as a demo for you, but obviously I'm not in class, and so we'll just kind of talk about it. So this example tells us, what if I add some HCl? Now, at first glance, I don't see any HCl here, right? So you'd say, oh, well, how would that affect anything? Well, what is HCl? HCl, when you put that in water, remember, dissociates into H plus and Cl minus, right? So HCl is a source of H pluses and Cl minuses. There are no H pluses here, but there are Cl minuses, right? So if I add HCl, I'm actually adding extra chloride ions here. So if this was at equilibrium and I add HCl, I'm disturbing it by adding more of my reactants. Now I have too many reactants, too many chlorides. What do I do to get rid of those chlorides? It shifts to the left. So shifts left to use up the extra Cl minuses. So what color is it going to become? Probably a more bluish. I apologize. I'm so sorry. It shifts right, not left. I apologize. That should be right. So let's go over this one again because I misspoke here and miswrote it as well. So if I have too much chloride, I want to use that up, and so it's going to shift to the right to use up my chloride. And so it shifts to the right to use up any extra chloride. So since shifting to the right, it is becoming more blue. So you will see more blue color. Probably still a shade of purple, but it's going to be a more bluish purple in this case. Okay, let's look at the next one. So what if the reaction was heated, and they're telling us that the reaction is endothermic? So if the reaction is endothermic, that means the heat is added on the reactant side. So I'm going to say plus heat on this side. So I heat my reaction, so I'm adding more heat here. So I have too much heat now, I need to get rid of that extra heat. And so what's going to happen, if I want to use up that extra heat, I'm going to shift to the right to use it up. And so it's going to again become more blue. So again, shifts right to use up heat. So it becomes more blue. All right, let's look at the next one. Silver nitrate was added. Now this, if this was on the test, it would give you a little bit more hints here because it's kind of hard to tell what silver nitrate does because there's no silver nitrate anywhere here. If you think about it, silver nitrate, you put in water, you get Ag pluses and NO3 minuses. We don't really have Ag pluses or NO3 minuses here or anything like that. However, if you remember from your solubility rules we learned a while ago, most chloride salts are soluble with a couple of exceptions. One of those exceptions was silver chloride. When you add Ag plus to Cl minus, they precipitate. They react together, clump together, and precipitate down as a solid that's not soluble. So again, on the test, if this was a question on the test, it would tell you, hey, AgCl precipitates or something like that, or Ag plus reacts with Cl minus to precipitate. And so basically what we're doing is, since we're adding Ag pluses, they are reacting with the Cl minuses and removing the Cl minuses from the solution. So what I'm doing is decreasing, lowering the amount of Cl minus that I have. So I've disturbed my equilibrium because now I don't have as much Cl minus as I need. So what do I do to make up for that lost Cl minus? It shifts to the left to make more Cl minus. So this one would be shifts left to make more Cl minus, so it's going to be more pink. Okay, last one. The reaction flask is placed in an ice bath. So if it is placed in an ice bath, remember we said that this was endothermic, so heat is on the reactant side. If I place it in an ice bath, that means I'm removing some of that heat. So now I don't have as much heat as I need. What do I do to make for that up? I shift to the left to make more heat, to produce more heat. So for this one, we'll say shifts left to produce more heat. And so it's going to become more pink. All right. There is a lab that we were supposed to do. It's called the Chatelier's Principal Lab. I'd like you to try to think through what do you think would happen. So it gives you a reaction, it gives you the different colors, and it tells you these are the different things that we're going to do to the reaction. Predict, is it going to shift to the right? Is it going to shift to the left? And what color would it become? And so it's kind of similar to this example here. So I'd like you to try it out, and then on Google Classroom, you will find the answer to the lab worksheet there, so you can kind of check your answers. So you can treat it as if it's another worksheet. All right. Hope you have a wonderful rest of your day.